volume expansion and linear expansion. Linear area and volume expansion of metal, well, we could say any solids, doesn't necessarily have to be metals, solids, liquids, and gases. Right? For solids, we have this equation. Delta L is equal to alpha L initial delta T, and alpha is called the coefficient of linear expansion. So the units of that would be, well, this is the change in length of an object. Is linearly proportional to the temperature change of the object and linearly proportional to the original length of the object. So delta L is in meters, L initial is in meters, and then delta T is in Celsius, and alpha is 1 over Celsius. By the way, a little bit of a note I want to make is that some equations we're going to use rely on the temperature of the system, and some equations will rely on change in temperature. Right? So in the ideal gas law, PV is nRT. This is not based on the change in temperature, it's the temperature itself. Whenever you have that kind of a law where the temperature is what's important, the temperature needs to be in Kelvin. It cannot be in Celsius. Right? Can't be in Celsius. Now you might say, weren't you using in Celsius in your videos to prove the ideal gas law? Yeah, I was kind of cheating. You're not supposed to use Celsius. But you can use Celsius to prove that the equation is true, that pressure is uniformly proportional to temperature and volume is uniformly proportional to temperature. You could use Celsius, but once you have a problem that asks what's the pressure of a gas at absolute zero, let's say, and it gives you the number of moles of the gas, or let's say it tells you what's the pressure of a gas at 0 Celsius, right? So let's say, suppose you were given the volume is 1 meter cubed and the temperature is 0 Celsius and the number of moles is 1 mole, and the problem asks you find the pressure of the gas, right? Of course you cannot do P times 1 is 1 times 8.3145, and then if you were to use Celsius you would put 0. That would mean the pressure of that gas is 0, and it cannot be, right? You have to, in that case you have to put Kelvin. So the temperatures you have to change to 273.15. Then you can find the pressure of that gas. The 1 mole of gas, which occupies a volume of 1 meter cubed, that's the pressure of that gas, you see. So any problem that gives you Celsius, always convert to Kelvin. But you could use it like in my videos, you could use the Celsius scale to prove the ideal gas law, then work backwards to calculate what absolute zero is. Then once you get absolute zero, the rest of all your equations, you should always do it in Kelvin. See? Now, equations that rely on delta T, you could do Celsius or Kelvin, right? Because why? You have a Kelvin is equal to Celsius plus 273. If you take the derivative of this, dk is dc. That means the unit change of Celsius is the same as unit change of Kelvin, right? So if you're running a fever of 1 degree Celsius, that means you're going from 37 to 38. A fever of 1 degree Celsius is equivalent to a fever of 1 degree Kelvin. So because then you're going to run from 310 to 311 on Kelvin, right? But Fahrenheit is different. Fahrenheit is 9/5 C plus 32. dF is equal to what? 9/5 dC. If you're running a fever of 1 degree Celsius, how much equivalent is that? 1 degree Celsius is equivalent to 9/5 Fahrenheit, right? So what would that be? 1.8, right? So if your normal body temperature is 37 and you are running a fever, you're 38, right? That would be equivalent to a person 98.6 of what? 1.8 plus this, right? Which would give you 99.6, 100.4. Oh, you see that? So 1 degree is more severe, 1 degree Celsius fever is more severe than 1 degree Fahrenheit fever. So 1 degree is equivalent to 1.8 Fahrenheit. So that's why you cannot use DF, you cannot use Fahrenheit pretty much in any of the equations we have. You cannot use Fahrenheit, you have to do Celsius or Kelvin. For delta T, you can do Celsius. So then the Celsius cancels the Celsius, and then you have meter equal meter. So the alpha coefficients of linear expansion is going to be usually given as 1 over Celsius. Coefficient of linear expansion. In our case, we are assuming that the coefficients of linear expansion are constant. That we're assuming that they're constant, but in reality, they are bit temperature dependent too. They're not really constants themselves. So you see here that the alpha of the material actually increases when the temperature increases. You see? In which case, if that was true, then you have to do integration. Okay, so these are the alphas of different materials, such as aluminum 21 to 24 times 10 to the minus 6. Aluminum. All these other materials, arsenic, amber, brass, 18 times 20. I'm putting the main metals, but 18 times 19 times 10 to the minus 6. Usually metals probably are expected to expand more because they are conductive, so their atoms are generally more looser, and so they can push on each other easier. See, 18 times 19, whereas this guy, let's say, amber is very big, 50 to 60. Let's see here. Celluloid, that fat pretty much? 100, oh, they're very big. Cellulose acetate, cellulose cement, 11, chromium, cobalt, 12, concrete, alpha of concrete. Diamond is not that big, huh? 13 to 14. Granite, 7.9. Iron, lead is 29. That's pretty big. Polycarbonate, 130. Silicon, silver, sodium, steel. Steel is not too big. Okay, then you have area expansion. In other words, linear coefficient of expansion is the linear expansion is just when you're assuming that the object is much longer than its width or its thickness. So let's say, for example, you take wood. When you heat this up, right? Notice its length is much bigger than its width or its thickness. So it really will experience length expansion, width expansion, and the thickness expansion. But the length expansion will dominate. So you can almost assume that this is expanding mostly in the length direction. You see? But then when you have, if the wood was more like a surface wood and the thickness was small, so then it dominates in the length and the width. But then if it's a box, then it's going to be three-dimensional. You see? So linear expansion is true when you're assuming that the width and the thickness are negligible compared to the length. You see? So what happens when you have a two-dimensional object, such as, for example, the tiles on the floor? When they're heated or cooled, what happens? They're mostly two-dimensional objects, right? They have a length and a width. So they're going to expand in the length and the width. So what do you need to put when you're putting tiles on the floor or on the kitchen counter? You need to put the space in between them, right? Take a look at the bottom of the ground. What's the space in between them filled with? Some material, right? What is that called? There you go. And there you go with the science of grouting. This is a big old science, right? When you're putting tiles, you have to put grouts in between so that you fill the space. It's like almost like a gum type material, right? Varieties. Grout varies including tiling grout, flooring grout, resin grout. Where do they get these from? Non-shrink grout, thixotropic grout, ketchup. So where do they get this from? It's a dense fluid which is used to fill gaps or used as a reinforcement in existing structures. Grout is generally a mixture of water, cement, and sand. Water, cement, and sand. It is employed in pressure grouting, embedding rebar and masonry, connecting sections of precast concrete, filling voids, and sealing joints, such as those between tiles. That allows the tile to expand and cool without cracking. You see? I hate putting grout because you do it, then you have to wash it right away so it doesn't stick to the tile, right? And then when you do grout, you also have to decide what color to do it, what material to do it. Okay, so when you do two-dimensional, then what is happening? Then let's say the width and the length, they're both increasing. So then when I heat it, what's going to happen? I could use the separate equation for the width increase, right? The width increases by a certain amount, and the length increases by a certain amount. But if the length is more than the width will increase more than the width increase, you see? So then what's going to happen here? The area final is going to be the final length times the final width, right? What's the final length? L initial plus delta L. What's the final width? W initial plus delta W, right? So then what happens? L initial, let's see here. L initial I could do L initial times W initial plus L initial times delta W plus delta L times W initial plus delta L times delta W. Simple binomial expansion, right? Then what are you going to get? L initial W initial is what? The initial area. And L initial times delta W, well, what's delta W? Well, remember the equation, delta L is this, and then delta W is going to be what? Delta W, alpha, W initial, delta T. So then if I put that here, alpha, W initial, delta T. Delta L is going to be alpha, L initial, delta T. W initial, plus delta L, delta W, alpha, L initial, delta T, alpha, W initial, delta T. So that tells me, what's this? A final minus A initial is delta A. Right? So what's this? Alpha, L initial, W initial is what? A initial. Alpha times L initial, W initial is A initial. But plus alpha squared, A initial, delta T squared. And then so what's going to happen? Delta A, 2 alpha A initial delta T plus alpha squared A initial delta T squared. Let's see here. If we Google area expansion of solids, see? Thermal expansion in 2 and 3 dimensions. Look at their equation. For small changes in temperature, temperature changes, the change in area is given by 2 alpha delta T, where A is the change in area. Oh, you know what? They forgot to write delta A here. They should have wrote delta A is 2 alpha delta T. Hold on. Delta A is equal to 2 alpha A delta T. They forgot to write the delta. So where are they getting the equation? So they're saying that if the temperature change is small, this dominates over this. Why? Well, because you got alpha squared here, right? What are typical alphas of materials? So look how small the alpha coefficients are. Coefficient of linear expansion, right? Remember 10 to the minus 6, 25 times 10 to the minus 6, 19 times 10 to the minus 6. They wrote it kind of weird. 3 times 10 to the minus 6 glass, right? 3 times 10 to the minus 6. So if the alpha is 10 to the minus 6, what's going to happen? This is 10 to the minus 6 squared, which is going to be 10 to the minus 12. Well, delta T has to be so large that squaring that helps make this a considerable number, right? So delta T would have to be like thousands and thousands in order for you to square them and for you to cancel that 10 to the minus 12 thing. So therefore, for most purposes, this can be ignored, right? So then what do you think is going to happen when we have volume expansion? When the height also is considerable, let's say H, the LWH, then you're going to have what? Volume expansion. right? L plus delta L, W plus delta W, H plus delta H. But from these consideration, what do you think is going to happen? You're going to have a similar equation that you're going to get, and then now you're going to have delta V is equal to 3 alpha V initial delta T, right? And then for the, you're going to have probably something like alpha squared. You're going to ignore that, you know. Let's see. See there? The change in volume is very nearly V is 3 alpha V delta T. You see 3 alpha. But then that 3 alpha they're deciding to call beta. And that is they're deciding to call it the volume expansion of a solid. Right? Beta. So therefore this is the volume expansion of a solid. So the beta of a solid is what? Roughly equal to 3 times its linear expansion. You see? So let's see if that's true. If we go to this table, this is material, aluminum, right? 25 times 10 to the minus 6. Coefficient of volume expansion for aluminum is what? 3 times that. So 75 times 10 to the minus 6. Right? 19 times 10 to the minus 6, 19 times 3, 57. That's a weird math, right? They should have had 57. 17 times 3, 51. 14 times 3, 42. Yeah, it matches. It should be 36 and so on. Okay, so the volume expansion is going to be 3 times. But so far this is just solids. For liquids, you don't have such a thing as linear expansion. Liquids and gases only have volume expansion. Right? So volume expansion of liquids and gases.